what does it really take to make a programming language? As a software engineer, I'm sure you've written code in languages like Python, JavaScript, Java, and more. But have you ever considered how that code gets turned into something that the computer can run? In this video, we're going to dig into how programming languages work and what it takes to build one from the ground up. We're going to go beyond the basics, so buckle up. Things are going to get a little more technical. Let's get the obvious question out of the way. What is a programming language? You probably already know that it's a set of instructions that tells the computer what to do, but let's break that down a little bit more. Computers operate on binary instructions. Everything boils down to ones and zeros, but humans, we don't think in binary. I mean, we can, it would just be very difficult. Binary additions and subtractions are already hard enough, talk less of doing more with binary. That's where programming languages come in. They bridge the gap between human thought and machine execution. Each programming language is essentially a well-defined system of rules that allows us to write human-readable instructions, which can then be converted into machine-executable instructions. There are hundreds of programming languages, each designed with a specific purpose in mind. The different languages provide different levels of abstraction from the underlying hardware, with hardware here meaning computers, web servers, mobile devices, IoT devices, and others. Some programming languages are built for system-level control, others for web development, game development, and so on. For example, if you're developing a website, you're probably going to work with HTML, CSS, JavaScript, or a JavaScript library. Developing for iOS, you probably want to use Swift, and for Android, Kotlin. If you're diving into AI and machine learning, you're likely going to use Python. And of course, for low-level control or embedded systems, you'll probably be working with languages like C, C++, or even assembly. These languages aren't just random choices. They're all designed to make certain types of programming tasks easier or more efficient. The abstraction level of each language dictates how much control you have over the hardware versus how much the language does for you. But how do these languages actually work? What happens when you write code and press run? Let's get technical. Say you're writing a simple Python program to calculate interest. The Python code might look something like this. Easy enough. You define your variables, write a method that houses the formula, and Python handles the rest. But under the hood, a lot is happening. Python is an interpreted language, meaning there is no separate compilation step. When you run this Python script, an interpreter takes your code and translates it line by line into machine instructions in real time. In contrast, compiled languages like C++ work differently. With compiled languages, you write your code and then pass it through a compiler before you can execute it. The compiler translates your high-level code into machine code all at once, producing an executable file. This file can be run directly by the computer's processor and is often faster than interpreted code because the translation is done ahead of time. Now, let's talk about what happens behind the scenes during this process. For compiled languages like C or C++, the first step in the compilation process is called pre-processing. During this phase, external dependencies are added, macros are expanded, comments are removed, and conditional compilation directives are processed, preparing the code for the actual compilation step. That's a lot, I know. Stick with me here. Next, the compiler translates the code into an intermediate representation, usually something like an abstract syntax tree, or AST for short. This AST breaks down your code into tokens and structures that reflect the logic of your program. Once you have the AST, the compiler then performs a variety of optimizations. This is where things get interesting. Modern compilers are very sophisticated. They'll do things like constant folding, dead code elimination, loop unrolling, and register allocations to make sure your code runs as efficiently as possible. After optimizations, the compiler then generates assembly code which is specific to the target architecture, for example x86 or ARM. Finally, this assembly is translated into machine code which the processor can execute. For interpreted languages like Python or JavaScript, there is no separate compilation step. Instead, an interpreter reads your code line by line. In Python's case, it's using a bytecode interpreter. When you run a Python program, it first compiles your code into bytecode, which is an intermediate form that is more abstract than machine code, but is closer to machine code than your original Python script. This bytecode is then executed by the Python virtual machine, or PVM for short, which is a runtime that interprets the bytecode and interfaces with the system's underlying hardware. Java is another interesting case because it's sort of a hybrid. When you execute a Java program, it first gets compiled into bytecode by the Java compiler. But this bytecode isn't specific to any one machine. It's meant to run on the Java virtual machine, or the JVM for short. The JVM is what makes Java write once, run anywhere, because the JVM can be implemented on many different platforms, and the bytecode will run the same regardless of whether you're on a Mac, Windows, or Linux. Now that we've covered how programming languages work, the next question we'll cover is, what does it take to make one? First off, you need to define the syntax. This is the grammar of your programming language, and it sets the rules that dictates how you write the code. You have to decide how its syntax works, from variable declarations to control structures like loops and if statements. For example, in Python, indentations define code blocks, whereas in C# or Java, you use curly braces. Next, you will need to define semantics. Semantics define the meaning of the syntax, the logic that the language follows when it executes the code. When you write if x is greater than 5, the language semantics determine what greater than means and what happens if this condition is true or false. Once you've got the syntax and the semantics down, you'll need a compiler or an interpreter. If you're creating a compiled language, you need to build a compiler that can take source code, break it down into tokens, generate an abstract syntax tree, optimize the code, and then output machine code. This involves building a lexer to break the code into tokens, a parser to turn those tokens into meaningful expressions, and a code generator to spit out machine code. If it's going to be an interpreted language, you're going to need an interpreter that can take the source code and translate it on the fly into something executable. This might involve compiling it into an intermediate form, like bytecode, or directly interpreting the high-level source code, depending on your design. On top of that, you'll need standard libraries. These libraries provide pre-built functions and classes that let developers perform common tasks without rewriting code from scratch. Think of things like reading and writing from files, networking, or even basic math operations like square roots. These libraries are key for making your language practical and usable. You also need some error handling. When developers make mistakes, they need clear error messages that help them debug their code. Designing how your language handles errors and warnings is critical to the user's experience. Some languages are more forgiving than others. Python, for instance, throws exceptions that are relatively easy to catch, while languages like C just crash if you're not careful with memory management. Last but not least, you'll need to do some optimizations. Optimizations are crucial. Whether you're writing a compiler or an interpreter, optimizing the way your language handles memory, CPU resources, and I/O operations is what separates sluggish languages from really fast ones. You'll need to decide what trade-offs are worth making, whether it's favoring speed and simplicity over memory efficiency. To wrap it all up, creating a programming language takes a deep understanding of both software design and how hardware works. You'll need to build everything from the syntax rules to the runtime environment, and you'll have to make countless decisions about what features to include, how to handle errors, and how to optimize for performance. It's no small task, but it's the foundation of everything we do as software engineers. That's it for this one. For those of you who are new here, my name is Uma. I am a software engineer, career coach, and a content creator. I enjoy learning and breaking down complex technical topics to make them easy for you to understand. I also coach software engineers to help them learn and increase their earning potential. If you'd like to work with me or check out my courses on Git, AWS, and other technical concepts, click the link in my bio or go to umacodes.com. If you enjoyed this video, don't forget to give it a thumbs up and subscribe for more videos like this. Thanks for watching, and I'll catch you in the next one. Peace.